On page 1, remember you can hit pause and rewind anytime you need, so I'm not going to slow down too much. We're going to prove the mass of the Earth. As it says, a number of different scenarios could do this, but if you know some true facts, any true facts about the relationship between the mass of an object and its weight on Earth, you can find the mass of the Earth. Remember, you don't have to remember formulas. There's a giant formulas and constants list that we've got going. We can hand it out as soon as possible. It's been triple checked. I think it's good. Here is our formula. Force between the two objects is equal to the gravitational constant. That's a given. That's that. Excuse me, it's that. We'll get there in a minute. Times the masses of the two objects and the radius between them, the distance really between them. This was figured out for rotating bodies and satellites and planets, so it was designated R, but it's really the distance between the centers of the objects. I'm going to pick M1 for mass of Earth. It doesn't matter which one you pick. I guess I'll pick M1. I guess I picked M2 actually. And I'm going to call this the mass of the Earth. Well, if I solve for that, that means that this goes under. This goes under. I have F over G M1, and this has got to go up, and R squared is on the top. R squared is on the top, F is on the top, G and M are on the bottom. I'm going to find the mass of the Earth, and I know it's a given on the constants paper, but I'm making you prove it. Here is my gravitational constant. Here's the distance between the objects. Because the object is on the surface of the Earth, this is the distance between the object and the Earth's core. This is the average or mean radius of the Earth, the distance from the core to the average surface. We're going to get numbers good enough for our book anyway. Here is the force between them, because we said it experiences a force of 58.8 newtons on the surface of the Earth. So that's F. Here's the gravitational constant. That's a given. Don't bother memorizing it. Just know how to use it. And here's the actual mass of the object. Remember, R is squared. So this squared times this, divided by this, gives me mass of Earth of the mass of Earth. Number 2. So Jupiter has a mean radius of this much from the Sun. Show the calculation for the orbital period in Earth years. This means the time of orbit for Jupiter over the time of orbit for Earth, all squared, so divide and squared, is equal to the radius of Jupiter from the Sun over the radius of Earth from the Sun, divide and cube. Of course, I don't know the time of Jupiter, that's the point. Show the calculation for its orbital period in Earth years. Now, I know the radius of Jupiter from the Sun, and I know the radius of Earth from the Sun. Averages, of course, as we've discussed, these are slightly elliptical. And I darn well know the time of orbit for Earth in Earth years. It's exactly 1 by definition. This divided by this cancels out the meters. This divided by this cubed gives me 139.5. 1 year squared is 1 year squared. I can pull this around and up. And now I have TJ, time of Jupiter squared, equals 139.5 times 1 year squared. Of course, times 1 is basically meaningless. When I square root both sides, I get 11.8, and the year squareds turn to just years. Number 3, we're going to find the, the time of orbit for a geosynchronous satellite. Okay, what I need is a few things here. I need to recognize this formula. Now, what I really stuck for, though, is this here. This is the radius, and it's the distance from the satellite to the core of Earth, which turns out to be a bit of a tricky point. I know the distance above the equator. That's to the surface. That doesn't count. That's not good enough. I need at least to get something reasonable. Here's my distance above the surface in meters. Notice the difference. Kilometers to meters. Add 3 zeros to get meters. It's 1,000 times more, right? Now, I need to add it to the internal radius of the Earth to get to the core, the distance to the core. And this is in E6, times 10 to the 6th. So even though it's not standard, I'm going to keep this in E6. So I'm going to go 1, 2, 3, 4, 5, 6, and I'm going to get 35.786 E6. That's not scientific notation, somebody will say. Yeah, I know, but I have to have these the same or they don't add. It's still true. Just because the decimal is not digit dot doesn't make it not true. So I can add these, and here's the distance from the center of the Earth to the satellite. That's an R I can use. So the time of the satellite is equal to 2 pi times the square root of all this. R, which I just figured here, the distance from the satellite to the core of Earth, cubed, over the gravitational constant, which we've seen before many times, and it's on the constants and formulas paper, and the mass of Earth, which is given, and in fact you figured it back at number 1. So this cubed gives me this, and the meters cubed is the units. Sorry, I'll run through some of that again. This is r cubed, that comes from here. 2 pi, this is r, this is g, look it up, and this is mass of the Earth that was given. This cubed is here, this times this is here. There's another meter in here, which means this all cancels out, and I end up actually with only all that remains is when I square root all this times this divided by this square rooted, all that remains is seconds. And it's a large number. What I want it in something usable. Let's not leave it in seconds. Let's get it in something people are used to using. If I divide by 24, I get hours, and if I divide by, if I divide by 3600, I get hours. That's what I mean to say, hours. Slightly under 24 hours, which is, actually goes back to number 7. What's your weight on Mercury's equator? Well, what's my actual mass? I know on Earth I have a force, a weight of 606 newtons. My mass is unknown, and I know on Earth I have a gravitational acceleration of 9.8 meters per second squared. This divides under, this divided by that gives me m, and I have a true mass of 61.86 kilograms, which is true no matter where I am in the universe. So, the force due to gravity will be the gravitational constant times the mass of me times the mass of Mercury over the distance from me to the core of Mercury, which is given up in the text. But I have to use it in meters. This has to be in meters, this has to be in meters, so stick 3 zeros on the kilometers. So, gravitational constant times my mass, which we figured out to the left, times the mass of Mercury, which was stated in the text, over the the distance between us, that is me and the center of Mercury, in meters, squared. So this times this times this divided by this divided by this, you can do it that way. That's the same thing as figuring out what it is squared. You can just divide by it twice. Should give you the force of your weight on the surface of Mercury. Except you'd burn up. Let's take the mass of the Sun. If somehow we know the mass of Mercury is this, it orbits in this distance and has a distance from the Sun of this. Let's put this in. Notice time must be in seconds. So, time for a satellite, Mercury is the satellite here, squared equals 4 pi squared r cubed over g, that's gravitational constant, times the mass of the thing being orbited. This is the mass of the Sun, not the mass of Mercury. Oh, as a matter of fact, I recall now that this is a distractor. Nobody really cares. That's not going to enter into it. The mass of the orbiting object is not part of the point. So mentally, scratch that out. It's not important. So let's solve for m. If n comes here, it goes up into the top as it goes through the equal sign. The t squared goes to the bottom to join g. So, the mass is 4 pi squared times the distance between me and Mercury and the Sun cubed. Gravitational constants here, and the time of rotation around the Sun, orbit of the Sun, around the Sun, is in seconds. Now, if it's given in days, you must multiply by 25 and then 3600 to get seconds. 24 times 24 will get you hours, times 3600 will get you seconds. That goes here. So this cubed times pi times 4 gives me this. This squared times this gives me this. And these conveniently cancel out, leaving me kilograms. So this divided by this is this.